Hi, I'm Patricia and I'm from Portugal. Almost 5 years ago, I started studying engineering physics at IST in Lisbon. Now, for my thesis, I'm working with Inês Kemen and Golb to develop and fabricate X-ray optics for 3D X-ray microscopy. The human eye can only see up to 100 micrometers, which is the diameter of a hair. Thanks to advances in microscopy, now we are able to see up to atomic resolution, and huge advances in science and technology were possible. It started with the optical microscope, which uses visible light and with which we can see things like cells and microorganisms. Advances in technology allow the resolution of the optical microscope to reach its maximum possible value of 200 nanometers. In order to obtain higher resolutions, we needed to use a different kind of light, with shorter wavelength, or even something that isn't light. That's when the electron microscope was invented. This kind of microscope uses an electron beam to probe the sample, and nowadays we can have up to 50 picometer resolution. Even though with the electron microscope we can achieve high resolutions, the samples often need special preparation, like metallization, cutting, or freezing. However, there's an alternative that can be used for high-resolution microscopy: X-rays. X-rays have much shorter wavelengths than visible light and have higher penetrating power than visible light and electron beams, allowing imaging inside the objects. With X-rays, we don't need special preparation to image samples, and so we can see the samples in their natural state, which is a big advantage in life sciences. Here at IST, we are working on a new idea for 3D X-ray microscopy in a project called Voxel. The idea is to combine X-rays with a technique used nowadays in 3D cameras called light field imaging. With this technique, we have an array of lenses that can capture in a single shot multiple point sources of light from an object. Then, by computer reconstruction, we can focus on different parts of the image and even create a 3D image. Since X-rays can enter inside the objects, with this technique we can capture a 3D image of the inside of an object with high resolution. The final goal of Voxel is to be able to provide computer tomography used in medicine. But first, we are working to demonstrate this technique to image smaller things, like small samples or animals. This kind of imaging requires the X-ray beam to be focused on the sample. For my thesis, I will fabricate lenses to focus X-rays for the Voxel project. X-rays don't interact with matter in the same way as visible light. Since most of the materials have a refractive index less than 1 for X-rays, we cannot use conventional focusing systems used for visible light, as they will actually cause X-rays to diverge instead of focusing. The simpler way to focus X-rays is with a type of lenses called Fresnel zone plates. This lenses' working principle is based on diffraction, and they are basically circular diffraction gratings with opaque and transparent zones, whose width decreases radially. When X-rays pass through them, they diffract, and interference zones are created where the X-ray waves can interfere either constructively or destructively. The zones are designed in order to block the destructive interferences, allowing only the constructive interferences to pass, creating a focus point. The final resolution obtained with this kind of lenses is approximately the width of the outermost zone. In order to achieve resolution of the order of nanometers, the dimensions of the Fresnel zone plates need to be on the nanoscale, and thus require nanofabrication techniques. I will fabricate the Fresnel zone plates in the clean room of Inês Kemen, using e-beam lithography, and then test them in the Voxel lab. If you want to know more about the Voxel project, you can go here. If you want to know more about Inês Kemen, you can go here. Bye!